Okay, so as promised, I said we shall start the next video by looking at trees. I'm very sure now most of you are starting to imagine which kind of mathematics this is. We are talking about trees, yes, even forests. We are going to look at forests, okay? But anyways, in this case, we're not looking at a tree like those trees outside which give us fruits. We are looking at a tree as a special kind of a graph. Actually, it is an undirected graph, meaning there are no arrows, and it has a property that any two vertices are connected by exactly one simple path. A path can be a group of edges, more than one edge. So with a tree, if you look at a graph, okay, which is a tree, and then say you want to consider two vertices. For example, let's look at a vertex V1 and V5. How can you connect the two? In how many ways can you be able to connect the two vertices, V1 and V5? So the only way is to move from here to through V4 through V5. There is no other way. Okay, the same applies to say V4 and V6. There's just one way, one path. So V4 through V5 and then to V6. So for any two vertices, there's exactly one path which you can use to connect the two. So for a graph with such property, then we say that that graph is a tree. We have some examples here. You can have a tree on one vertex that we don't have any edge. If you have two vertices, there's just one edge connecting the two vertices. You don't have any other alternative edge. For example, if we added another curved edge from here going to this second one, then that would not be a tree. The third example of a tree on three vertices, you just have one edge connecting each of the vertices. You don't have any edge, say from the first one to the third or from the second to the third. No, it's just one edge between any two vertices. So in this case, between the first vertex and the second, you have to move through between first vertex and the third. If you want to move from the first vertex to the third, in example 3 here, you have to pass through the second vertex. There is no other way out. So these are some of the examples of trees. You can try to look at these remaining examples. This is a tree on 5 vertices. There are some 3 examples here on 6 vertices. These are the examples on 6 vertices. Okay. Yeah, so those are examples of a tree. First of all, I want you to know that it is an undirected graph. There are no arrows, and between any two vertices, there is exactly one path that can connect those vertices. Okay, there is no other way. Okay, finally, let me just conclude with this example. We have this vertex and this. How can you move, say, from this upper vertex to this downer one? You move from the upper one, come, pass through that vertex, pass through that, and then come here. There is no other alternative route to move from this vertex to this one. So this qualifies to be a tree. Okay, and these trees are very, very crucial in computer science and in mathematics, and a branch of mathematics which we call graph theory. Though in computer science they always write trees, or they write them as directed graphs with some edges and having some arrows, but in mathematics we prefer using trees as undirected graphs. Okay, and there is an example of tree, or let me call it a types of trees. We have two types. We have the rooted tree and the unrooted tree, and the difference is in the definition here, where we are saying that if one vertex of a tree is singled out as a starting point and all other branches fan out from this vertex, then you call such a tree a rooted tree. For example, here, if you look at, say, this vertex here, and suppose you want to move from this vertex to the blue one, there is only one route or one path which you can take, and that is from the root here, the blue one, you come, pass through this vertex, pass through this, finite to this. So this qualifies to be a tree, but realize that it has a property that one root has been singled out, that is one vertex, which we call the root, has been singled out, and all the other paths are originating from there. So if you have such a tree, then you call it a rooted tree. If it doesn't have such a property that one vertex is singled out and the others are coming from there, then we call it a non-rooted tree. So this tree is rooted because you have this vertex and everything else is stemming from there. So in the context of trees, yeah, you can say that this is the root, because if you have a tree in real life, for example, the roots, the growth of a tree will start from the roots, and then leaves, stems, and so on will come from there. Oh, there's one terminology which I forgot to tell you, and that is forest. So if you have a group of trees, then we shall call it a forest. For example, this tree, this tree, this tree, these three form a forest of trees having 5 vertices. A forest of trees having 4 vertices, for example. Okay? Yeah. So that's all with the rooted trees. For a rooted tree, you have one vertex singled out, and all the other vertices come from that one vertex through the means of the connecting edges. So, for example, in this case, we shall say that this is a branch and this is also a branch. So this root has 2 branches, and when it reaches here, this root, this vertex now also has 2 branches. So when it comes to the notion of rooted trees, then we refer to the edges mostly as like branches. You have a vertex and then a branch. Okay? Yeah. So there are also what we call binary trees. A binary tree is a rooted tree, but with which property? Here is an example. We have a root. So binary means that every root, apart from the last ones, so every root of vertex will have 2 edges coming from it or connecting to it. So in this case, we have this 2, then there are 2 edges, get 5 here, we have 6 here, then 2 edges, 7, 8, then 5 has 2 edges as well, 1 and 4. So every vertex here has 2 edges connecting to it. So such a tree, we call it a binary tree, and these last vertices we call them the leaves. So the leaves of this binary tree are 1, 4, 7, and 8. Okay, so these binary trees have a lot of applications in computer science and, for example, in the storage of data in a computer. So, for example, if you have a list of, say, these numbers, so these numbers in computer like programming can be stored in different ways, and each mode of storage depends on which kind of tasks that you want to execute. So if I tell you that, okay, these numbers have been represented using a tree, a binary tree of this form, but if I tell you that this list here, the way this has been drawn, is also a representation of a binary tree. They are the same numbers, 1, 5, 4, 2, 7, 6, 8. We have 1, 5, 4, 2, 7, 6, 8. 1, 5, 4, 2, 7, 6, 8. So when you look at this list here, it's just a vertical arrangement of all the vertices. You can see that they begin from one of these branches, which is 1, 5, 4. So you have 1, 5, 4, then you write the root, and then 7, 6, 8, which is here 7, 6, 8. So binary trees can be represented in different ways, hence confirming that they really have like applications in the storage of data, since data can be stored in different ways or methods. So I don't really want to go into the details of the data storage and so on. I'm more interested in the basic concepts. At least you should know that what trees are, the different types, and where they can be used in the applications. And since by definition we saw that trees have a property that any two vertices are connected by exactly one simple path, so that tells you that when it comes to, say, if you have a problem of finding the shortest distance, then trees are very, very crucial. Yeah, and that's what this example is trying to explain. So suppose you have this binary tree with Q. You want to move from Q to, say, okay, H. You want to move or to traverse through the different vertices of this tree, but you're interested in finding the shortest distance. So given a set of vertices, if you want to find the shortest distance between them, then trees or binary trees are mostly used in finding, say, shortest distances for different problems. There are many problems on that, finding shortest distances, or if you want to maximize profits, you have a company and you want to maximize profits. That means if you want to get more profits in your company, for example, you want more production and less production time, because the more the time of production, that means the more costs you incur, for example, the labor, electricity, and so on. So you want to use as minimal time as possible. So such problems, most of the mathematicians always apply the knowledge of trees or binary trees to model such problems. So I just want you to have an idea, though I'll not go into the details. Okay. So we have another terminology here which you can use, or which you always come across when it comes to graphs, and that is a circuit. So we say that a graph has a circuit if you can move from one vertex to another without backtracking any edge. Backtracking means you don't go back to the edge where you already passed. Okay? We can try to look at this graph and see how can we move through all these vertices but without repeating or going back to any edge which you have already used. One way, for example, In this case, you can move from E to A to B to C to D to A to F. We've not repeated any edge. Another way can be to move from F to A to D to C to B to A to F. We've not yet repeated any edge. Are there any other possible such paths? So we can say that this graph indeed has a circuit because we've already found two. Yeah, so I want you to look at it and see if it's possible to find a third circuit. Okay, so this just talks about an application of trees where I was telling you about the shortest time, shortest distance, and so on. So you can just ignore this and just have the main idea where the trees can be applied in general. Okay, so let's now look at what we call directed graphs. Sometimes they are called digraphs. With this, you already have an idea, and we already said that a digraph, that is a tree in which the edges show direction. The edges are like arrows, and sometimes those arrows we call them arcs. Okay, so let me see here what happened. An arc. Okay, so for directed graphs we look at vertices and the edges are like arcs. Arcs are just edges with arrows. Okay, so if you have a vertex A and a vertex F and you have an arrow from A to F, then we say A is incident to F. Okay, yeah, then we also have what we call in degree and out degree of a vertex. What does it mean? Excuse me. So in degree of a vertex is the number of arrows pointing into the vertex, which means the number of arrows coming into that vertex. For example, A has how many arrows pointing to it? It has this and this. So we say that A has in degree 2, and there's also what we call out degree. This is the number of arrows pointing out from the vertex. So A has one arrow pointing away from it, so we say A has out degree 1. How about F? F has in degree 1 because there is one arrow pointing to it, right? And X has in degree 0 because there is no arrow pointing to it, and X has out degree 1 because there is one arrow pointing away from it. Okay, then another terminology which you'll come across when it comes to directed graphs is a path. Okay, and what is a path? We are saying that a path from vertex Q to vertex A is a sequence of arcs starting from Q and ending at A, in which no arc is repeated, and each vertex in the sequence is incident to the next one. It means that direction is very important. Yeah, you follow the direction of the arrows. For example, let's look at this. For instance, QXA. Let's see. QXA. You see, following the direction of the arrows, then we say that QXA is a path. Another path could be QXF, right? Yeah. Then you can also have QA, that is just a path was just maybe say just one arc. And we're also saying that XQA is not a path from X to A. Let's see, XQA. This is not a path because according to the arrows, it shows that X should come after Q. But when you say XQA, then you're trying to oppose the direction which is in the graph. So you say this XQA is not a graph. Okay, you read through the definition slowly, read through the notes, and you understand. Then you have another terminology which is a cycle. We say that in a directed graph, a cycle is a path that starts and ends at the same vertex. For example, AFXA is a cycle. Let's see. It starts and ends at the same vertex. So following the directions still, we have AFXA. So we have a path, rather a cycle from A back to A, following these arrows. So my question is, can you be able to identify any other cycles from this graph? Try to look at it again and see if you can find other cycles. And digraphs, project digraphs. Now this is also an application, and as I was telling you when I was introducing trees, that under trees are mostly applied when it comes to finding, say, shortest distance. So the same applies to the project directed graphs. There are very many applications, and they are the ones which are being talked about here. But in our case, my main point of interest for the case of year ones is going to be the mathematical bit of it, the simple mathematical bit of the directed graphs. So with these directed graphs, I don't know whether you've come across what we call matrices. We can be able to interpret directed graphs as just a simple item in mathematics, and that is through analyzing them as matrices. And the idea is to first of all write, okay, I'll use this example here. All these are applications, but this is the main point that I want you to get. The practical example of a directed graph. So pictured below are paths that a helicopter flew during its journey throughout the city. So you have a city, and maybe these are 4 different centers. We have A, B, C, and D. So the helicopter flew from A to B, then from B to C, from C to D, and then D to A. So we can be able to represent that kind of movement using what you call the matrix representation of the flight of the helicopter. How? You just write all the cities, first of all, as rows. You write them like in this form, horizontally, and you also write them vertically. And you put a 1 if there is a directed arrow from one vertex to another. For example, here, from A to A, there is no arrow between A and A, so you put a 0. From A to B, look back at your graph. Did the helicopter fly from A to B? Yes, there is an arrow from A to B, so you put a 1 here. From A to C, 0. A to D, 0. From B to C, for example, there is an arrow from B to C, as you can see from the graph here. B to C, there is an arrow, so you put a 1. Also from C to D, you put a 1. Also from D to A, you put a 1. That's why you have a 1 here. C to D, there is a 1 here. B to C, there is a 1 here. So this is the graph corresponding to the movement or the flight of the helicopter. Yeah. So I just want you to note that there are many, like, directed graphs have a very rich structure when it comes to mathematics. There are many interpretations that can be got. So you can see from here, we've been able to obtain this matrix, and you can find that this matrix has a lot of other implications, and a lot of other ideas can be generated just from this matrix. So that's all I wanted to share with you. So from this topic of graphs, you need to know what a graph is, types of graphs. We have the directed and the undirected graph. Then we have trees, we have the rooted and unrooted trees. You should be able to give definitions, give examples, and then look at those different definitions that we've seen and make yourself familiar with them. So that's all for this video and this topic. Our next topic will be on permutations mostly. I'm going to make the notes and I'll be sending the video to you soon. Okay, I hope you enjoy yourselves with the videos.